All right, section 14.3. Let's do applications of vector of the calculus of vector valued functions. Well, so as I already gave you the heads up for this, so the given vector valued function means position. We take the derivative that gives us the velocity vector, and the second derivative gives us the acceleration vector associated with a given vector valued function, and then we are going to use vector valued functions to analyze projectile motion. So those formulas that you know from physics about projectile motion, all that you may be just given. Well, we're going to get them from scratch using vector valued functions. I'm going to derive that vector valued function. It's going to be pretty cool stuff. All right. Well, again, we already discussed a little bit of this. So we're given a vector valued function in the plane or potentially in space. So this is not limited for just a plane, for vectors in plane, also for vectors in space. The velocity, it's the derivative. The second derivative is the acceleration. But there's a little more. There's one more piece of information, that is the magnitude of the velocity, which represents the speed. Recall that speed is not the same as velocity. While the velocity indicates a direction, the speed is just a module, it's just a magnitude, how fast it's an object moving, but without caring about the direction. Okay, so for example number 1, find the vector velocity, the acceleration, the velocity vector, the acceleration vector, and the speed function. Notice it's not a vector, it's a function for a particle moving along the curve described by r of t, given all this madness here. All right. So because we're going to do a bunch of differentiation, notice how we're given radicals in the denominator. So I would rewrite the vector valued function in terms that we can easily differentiate. That is t to the negative 1/2 2t plus 1 t e to the t minus 4. Okay, so all right. So number 1, let's find the velocity vector. Let's take the derivative v of t. That is, we need t to the negative 1/2. Take the derivative. That is negative 1/2 t to the negative 3/2. Okay. The derivative of 2t plus 1, that's simply 2. And the derivative, t e to the t minus 4. Which differentiation rule do you think we should use here? Chain rule. What is that again? Product rule, right? Product rule. That is the derivative of t, which is 1 times the exponential e to the t minus 4 plus the derivative of the exponential. Well, the derivative of the exponent t minus 4, it's still just once. It's just going to go itself, e to the t minus 4 times t, which I'm going to just put in here. All right. So that is our first derivative. Let me just clean up the 1 as a coefficient. So that'll be negative 1/2 t to the negative 3/2, comma 2, comma e to the t minus 4 plus t e to the t minus 4. Okay, so all right. So that's the first derivative, that's the velocity function. Let's get the acceleration function. That is the second derivative. Okay, the derivative, 3/2 times 1/2. That's going to give us what? 3 times 1, which is 3, 2 times 2, which is 4, 3/4. And also positive, because negative times a negative equals to positive. So t to the, negative 3/2 minus 1, isn't that negative 5/2? And the derivative of 2, that's 0. And then, well, again, the derivative of e to the t minus 4, it's just itself, e to the t minus 4. Plus the derivative of t e to the t minus 4. Well, isn't that differentiating that product again, which actually gave us the same result here? Well, I'm just going to copy this result plus e to the t minus 4 plus t e to the t minus 4. However, how about we combine like terms? That is, okay, 3/4 t to the negative 5 halves, 0, and combining these two together, that's 2e to the t minus 4 plus t e to the t minus 4. Okay? So that's our acceleration vector. All right. What else are they asking us for? Oh, the speed function. Okay, speed. That is the magnitude of the velocity function, or the magnitude of the first derivative, either way, right? So the speed, which is the magnitude, that is the square root of the squares of these three components here. Yes, it's going to look ugly. 1/2 t e to the negative 3 halves quantity squared plus 2 squared plus e to the t minus 4 plus t e to the t minus 4, all this madness squared, and then take the square root of all this madness here. Well, there's no need to simplify. I don't see the point, because we have combinations of exponentials, rational exponents with negative exponents and constants, but still you might want to clean up a little bit. There's not much to do, but at least clean it like this. Okay, so here, number one, this negative 1/2 squared is going to give us a positive 1/4 t. By the way, where did I get this 3? Yep. Just this, all right? And well, careful here, because 3/2 raised to the second power, power of another power, multiply the powers, multiply 3/2 times 2, essentially the 2's go away, leaving us with the negative 3. Okay, so that's what we can do. Negative 3, 2 squared, that equals to 4, and this, just leave it squared. E to the t minus 4 plus t e to the t minus 4 quantity squared. So this is good enough for the speed function, because again, I mean, you could write the t to the negative 3 in the denominator with positive exponent, and then what could we do? Maybe least common denominator to combine it into a single fraction, but that's not going to simplify that much. That's not going to help that much. So this is good. Okay, so we got the three functions: velocity, acceleration, and speed. Now they're asking us to evaluate these three when t equals to 1. That is, v of 1, which is the square root of negative 1/2 1 to the negative 3 halves, 2, simply 2 because there's no t's to substitute the 1, and then e to the 1 minus 4 plus 1 times e to the 1 minus 4. And leave this result in exact form. No need to compute the e's. So negative 1/2 times, okay, 1 raised to any power except, well, possibly 0. That could be an indeterminate form. So that's going to be negative 1/2. Then 2. And e to the 1 minus 4, that's e to the negative 3. Plus 1 times another e to the negative 3. Which combined together, the z component only, that's 1/2, 2, and then 2 e to the negative 3. Right? So that's the velocity vector when t equals to 1. All right? So a of 1, the acceleration at 1, that equals, okay, let's go with the acceleration, that is 3/4 times 1 to the negative 5 halves, 0, 2 e to the 1 minus 4 plus 1 e to the 1 minus 4. And that equals, again, 1 raised to this weird fraction, negative 5 halves. That's still 1. 1 times 3/4. That's just, again, a 3/4. 0. And here, 2e to the 1 minus 4, that's 2e to the third plus 1e to the third. And combined together, 3/4, 0, 3e to the third. Okay? So that is our acceleration vector when t equals to 1. What else we need? The speed, which is the magnitude of the velocity. Again, they're not the same result. While the velocity is a vector, the speed is a scalar. Okay? So speed, v at 1, that's the square root of all this madness here evaluated at, what's that, at 1. That is 1/4 times 1 to the negative 3 plus 4 plus e to the 1 minus 4 plus 1 times e to the 1 minus 4, and then squared. No, don't square the binomial. Pam does it. Do the inside of the parentheses and then square. So this will give us, well, number 1, the square root of 1 to the negative 3, which is still 1 times 1/4. That is 1/4 plus 4. And that is plus, how about this guy right here is 2 times e to the third power? And 2e to the third? Oh, negative third, right? Negative third. Thank you. And that is 1/4 plus 4. How about combine it together to get 17/4? And in this case, careful. Raise the 2 and multiply the exponent. So that is 4 e to the negative 6. So that is the magnitude of the velocity, also known as the speed. All right. So this is how we put this together. But now we put in the physics context, the velocity, the acceleration, you know. Okay, what's next? On the next page, I'm going to skip this exercise, this example, because we already did one like this in which we graph the vector valued function. And we put the acceleration vector and the velocity vector together at the given point where we have 4, 2. So we already did something like this. So let's move to, I should have gotten rid of this example on the notes. Okay. Anyway, example number 3. So we're given an acceleration vector. We're given an acceleration vector below this one. And we're given an initial velocity, which is this initial velocity, and an initial position as vectors. So, again, in the same way we went f of x, f prime of x, f double prime of x, that is position, velocity, acceleration. Now we're going to go backwards. Remember how we solved this initial value problem where we retrieved the constant of integration? So we did the antiderivative and then we got that constant of integration. But this time we're going to do it twice. All right, so we're going to go from acceleration to velocity and then from velocity to position. Okay, so what does that mean? Okay, so we're going to start with the acceleration. So now, instead of going in this direction, we're going to go backwards to go from acceleration to retrieve back the position. All right. Although these are going to be very simple integration situations, it's more about the notation, how we present the work. So for instance, we're going to go from acceleration to velocity by number 1 saying velocity equals the integral of the acceleration. And we're given that acceleration as a vector. All right? So that is the integral of 0, 18 dt And in this case, we don't know limits of integration actually because we're given initial conditions, that is initial velocity and initial position. Okay? So let's integrate. Okay, the integral of what's the integral of 0 by the way? Huh?
0.
0 plus the constant of integration, right? Because I mean, integrate 0 dt. Take the 0 outside if you want. This integral dt, that is 0 times t plus c. But 0 times t, isn't that just c? So, but in this case, because we have two components of a vector, we're going to get c1 and c2 respectively, one for each. So that is c1, comma, the integral of 18, that is 18t plus c2. Okay? All right, so what are we going to do here? So that means this is v of t, that's the velocity, equals to c1, comma, 18t plus c2. Okay, so we're going to use the initial condition, but which initial condition? That involving the velocity, the initial velocity, which is denoted with u naught v naught, that is 0, 9. Okay, so that means we're going to evaluate v at 0. Why at 0, you might ask? Because it's initial velocity, right? If it were at a different position, well, it would be given a value for t. But in this case, it's 0 because it's initial. For the first component, just c1, and then 18 times 0 plus c2. But again, this is a vector equal to a single quantity. But what is that single quantity? That's the given vector, okay? Because this is v naught, that is 0, 9. That is c1, 18 times 0, which is simply 0 plus c2, right? And again, two vectors are equal if their components are equal. We use that property of vectors to find to equate components. This means 0 equals to c1 and 9 equals to c2. So c1 equals to 0, c2 equals to 9. All right? Now here is the thing. We're going to go back to the velocity function right here and call this v of t equal to, what is that? c1, which is 0, comma, 18t plus c2. But this 18t plus c2, what did we get? Is that a 9? Okay? So we're just halfway through the problem. We just got from the acceleration back to the velocity. Let's do a second iteration of this problem now to go from the velocity to the position. Now, how do we express this formally first? Number one, r of t, which is the position, that is the integral of the velocity. Because again, we're doing this backwards. We're not going like we did before from position to velocity and then from velocity to acceleration. Now we're going back. We're integrating, which is the opposite of the derivative. Okay, so we need to integrate the vector we just got in the previous part. 0, 18t plus 9 dt. All right, so again, hey, what's going on? Hey, there you go. Again, the integral of 0, what's that again?
C1.
Okay, here is the thing. We already used the letter c, right? So to make a distinction between the constants of integration we use to go from the acceleration to the velocity, let's use a different letter to go from velocity to position. Try not to use the same letter because even though it could be the same result, we may get different results. So let me use in this case K1. Or you could use C11 or C12, I don't know. Just as long as it's not the same symbol. And then this will be the integral of 18t, that's, what's that? 9t squared plus 9t plus k2. Okay? So, r of 0, that is for the initial position. I'm going to evaluate, okay, this is simply k1, comma, 9 0 times 0 squared plus 9 times 0 plus k2. And r of 0, what is that r of 0 equal to? In this case, it's equal to the initial position vector. That is 7, negative 4. 7, negative 4. That is k1. This is all 0 plus, and this is simply k2. Again, two vectors are equal if their components are equal. That is, k1 equals to 7 by equating coefficients, or rather components, and k2 equals to negative 4. All right? So, and lastly, all we need to do is go back to the original function r of t, which is equal to k1, which is 7, comma 9t squared plus 9t, plus k2, which is actually minus 4, right? And that is our final answer. Now, take the first derivative and then the second derivative of this. You should get the original vector. What is that? 0, 18, right? Okay, guys, let's see what's next.